Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 4, Electricity and Magnetism. I'm going to be covering Inquiry Question 3, Magnetism, and we're going to be looking at the following dot point concepts. So for this lesson, our intention is to investigate the process in which ferromagnetic materials become magnetized, and our success criteria is to describe the force of interaction between ferromagnetic materials. If you want additional reading for this particular concept, here's the textbook reference. So, let's firstly start. What is magnetism? Now, magnetism is a physical phenomenon caused by magnets that results in a field that either interacts or repels with other magnetic materials. So, examples of where we can see interactions of magnetism, you have two bar magnets. As you can see, if we have an attraction, the magnetic fields join together. If there is repulsion, you can see there's an isotope line forming there. One of the biggest magnets that we have in the universe, or at least within our solar system, is the magnetic field generated by our planet. For those who don't know, the reason why we have this magnetic field is because of the iron core that's inside our planet. And that actually gives us the ability to generate magnetic fields, which is quite important because it actually helps block out solar wind from the sun. Depicting magnetic field strength. We said that the SI units to measure magnetic field strength is Tesla. Symbol to register what magnetic field strength is capital B. In most situations, we measure magnetic field strength in the frame of milliteslas or microteslas, which means that 1 Tesla is an incredibly large number for our everyday circumstance. When interpreting magnetic field diagrams, we know that the field strength is directly related to the amount of flux lines. The more densely packed the flux lines are, the stronger the field. The less of the flux lines, the lower the strength. One of the things we know that allows for magnetic fields to be generated is a quantum mechanic property known as spin. Now, spin isn't quite the same way that you recognize it in Newtonian physics, where you are just rotating around in a circle. Quantum spin is quite a different kind of idea. But you don't really need to know how specifically quantum spin works to understand how magnetic fields are generated. So, just to put a simple note, this allows particles to generate its own magnetic field. Okay? Spin can come in two states. So, for example, an electron, it has two quantum states, or two quantum spins. One that registers as plus 1.5, and then one is negative 1.5, or a half. So that's the property that dictates that a magnetic field will be generated. So in terms of the origin of magnetism, like we said, it's down to the quantum mechanics of spin. Now, electrons can have an up spin or a down spin. Their orbital motion can contribute to magnetic fields as well, but the quantum mechanic property is the main defining factor in this case here. If electrons are paired up, then their magnetic fields will cancel out. What we mean by that is, imagine we have an atom in an electron shell. If we just have one electron spinning in one direction, it will have the property of generating its magnetic field. Okay, so we'll just write B field induced. But if we have the case where the two electrons were in the same orbit, like so, we would get cancellation. Alright, so what materials can be magnetic? Now, materials such as iron, nickel, and cobalt, they have a rare magnetic behavior known as ferromagnetism. Ferromagnetism is a material's ability to become magnetized and induce its own magnetic field. In terms of the wording, ferro actually stands for iron. So when we mean ferromagnetism, it means a behavior similar to iron. So nickel and cobalt have the potential to behave quite similarly to iron, like so. Okay, this is like a nice little image that dictates how ferromagnetism will begin. You can think of these little components, each component here, known as a domain. So inside every material, assuming that they have these unpaired electron spins, they will have its own particular orientation. Now each component, we can call it a domain. Now the important part is, the reason why iron and cobalt and nickel are normally not magnetic is because the domains, as you can see here, aren't aligned. So domains not aligned. So what's the consequence of the domains not being aligned? Well, that will end up being same thing like we said before. Domains cancel each other out, so they cancel each other out. And there is no net magnetic field direction induced from this. Okay, so that's why under normal circumstances you don't see iron being magnetic unless you put a magnet next to the iron. And this is the beauty of ferromagnets. It does have an internal magnetic field, but it won't work unless it's exposed to an external magnetic field. What's actually happening, as you can see with our GIF animation here, once I put a magnetic field into this material, it causes the poles, or the domains we call them, to align with the direction with the magnetic field. So the domains inside the material will align parallel to the external field. Okay, so when this alignment occurs, okay, our ferromagnetic material is now magnetized. Okay, so that's what we can have there. So, same idea, let's have a look. Under normal circumstances, any ferromagnetic material, the domains are randomly orientated, and so that usually causes a cancellation of the material's magnetization. But when an external field is put into it, we can cause the magnetic domains to align with each other, and that's the thing that gives the magnetic properties. If you actually think about how a bar magnet works, it actually follows a very similar idea. So if I have a normal regular bar magnet, we have north and we have south. We always say that the magnetic field goes from north to south, so it goes in this kind of orientation here, like so. Now if you think about it, if it goes from in and out, then there must be something going on in this in between the bar magnets. So it's actually, what's actually happening is the magnetic field is traveling parallel in that way through the bar. So that's quite similar to what's actually happening in our domains here. Okay, so there's that. When iron becomes magnetized, the domains line up in the direction of the external field. Note that the north of each domain is repelled by the north of the external as this lines up occurs. So there we go. Alright, so let's just do a little quick summary of what we talked about firstly. A phenomena at the atomic level which causes unpaired electron spins to line up parallel to each other is called a domain. Okay, so to have the domain, you have unpaired electron spins. When exposed to an external magnetic field, an unpaired or a unparallel or unpaired, sorry, the unpaired electron spin aligns in the same direction, generating their own magnetic field. Once magnetized, the magnet will tend to maintain its magnetism, known by this term here. So if it's a ferromagnet, once you magnetize it, it also stays magnetized. That's also one of its key properties there. So let's have a look at where ferromagnetism can work. So where can we magnetize things to cause applications? The first one we have is the Maglev Trains. You might kind of remember this from The Simpsons. The idea is very simple. So the Maglev train, mag represents magnets, lev means levitation. And if you actually have a look at the train that we have here, so in terms of levitation, the train will levitate because of a strong repulsion force between the tracks and the train. Now, how do we get these magnets to do this? We actually use things called electromagnets. If you remember, electromagnets are magnetic fields that can be induced by electric current. So we actually generate a really high voltage AC electricity to generate this kind of levitation like so. In order to propel the train, we actually cause a really strong attraction and repulsion. So every time the train is moving along the track, if the front of the train has a north pole, right in front of it on the track, it will be a south pole. That's going to attract it forwards. Okay. Right behind that pole, there's going to be another pole that's exactly the same of it. So if we have two of the same pole types, that's going to cause a repulsion force, and that's also going to propel it forwards. So that's actually the application of how maglev trains work. Obviously, we don't have this in Australia, so I'm dying to hope for one day to get one of these. Next one we have is scrap metal collection. So as you can see here, we actually have a really large electromagnet, and that is induced with a strong DC power source, so direct current. That's going to cause the electromagnet to become magnetized, and that causes attraction on all these iron scrap metals. Obviously, this is a great application because you can drag a lot more scrap metal and then deposit it elsewhere. Another one you can actually try at home is to make your own electromagnet or maglev train. So a smaller version of that. All you need is a bit of copper wire, a battery, and two magnets. Obviously the magnets you use here, we actually call them neodymium magnets, so they're quite strong. Neodymium? Neomagnets, let's just call it that. And what's actually happening here, as the battery is moving across the wire, it's actually inducing electricity in the wire that then creates a magnetic field that propels our magnet forwards. We do talk about this a little bit more in module 6. This is due to Faraday and Lenz's law. And it's what we call electromagnetic induction. So we're actually, by having our magnet move through this copper wire, we actually induce a magnetic field that's going to drag the battery along with it and causes this circular pathway or this particular motion there. So if you have these resources at home, by all means try it out. Okay, so let's look at a question. The diagram below shows a coil of wire wrapped around a soft iron core connected to a power source. Firstly, find the direction of the current flowing through the circuit, and then the north and south poles of the electromagnet, and also the direction the magnetic domains are in. Okay, so to start ourselves off, let's firstly identify the direction the current is moving in. If we have a look at this particular component here, so that's our power source, or the cell in this case, the longer hand always represents the positive component. The shorter hand always represents the negative component. So my current is going in this particular direction, loops down like that, loops down like that, like that. So what you're seeing is it should be looping from what you're seeing in the screen in an anti-clockwise direction. Okay. And the next one we need to work out is the north and south poles of the electromagnet. So this is where you use the right hand grip rule. If you recall, drawing my right hand grip rule, my right thumb for a solenoid is the direction of the north pole. The direction that my fingers are curled in will be the direction of the conventional current. So if I have a look, what I want you to imagine is this part here. Imagine your fingers are these wires, so you're wrapping your fingers over the wire like so, and then have a look at where your thumb is pointing. Your right thumb should be pointing to the right. So the north pole is here, and our south pole is here. Let's see if we can show that on a simulation. Okay, so pretty much similar structure to what we have here. We said that the positive side is the positive side is the longer hand, so the current is going down like so. So if I actually use the right hand grip rule, you can actually see how I can picture this. So my fingers are coming down like so, similar to the diagram. My right thumb is pointing to the right, hence this is our north pole here. Okay. And the last component is to work out the direction of the domains. So just to help you picture it, if it's going north, it's coming out like so. If it's south, it's coming in like so. So we want to find a connector point in between. So in the connection point, we should find our domain lines to go like so. So these are our little domains that are going through the solenoid here. And that's how you go through this question. Okay, so another thing, there are other types of magnets. We have besides ferromagnets, they are quite rare. There are other two types. One is called diamagnetic or diamagnetism. So we have no unpaired electrons. And then we have paramagnetic. So within the electron shell of an atom, there is at least one unpaired electron. So what do we get? If something is diamagnetic, the spin alignment, when with the magnetic field exposed, it's going to go in the opposite direction of where the magnetic field goes. So there is a repulsion, as you can imagine. If we have paramagnetic, if it's aligned with a magnetic field, we have a attraction because their arrangement is going to be parallel with the direction of the magnetic field. So with diamagnets, we have a very weak repulsion. Paramagnets, we have an attraction. Still relatively weak, but an attraction. In terms of what happens to the magnetic field lines, if the field lines go through a diamagnet, it's going to cause a slight distortion or disjointness of the magnetic field. It's going to cause it to push out. And actually there's a really interesting application when this happens that we'll talk about in a second. While as with paramagnets, we squeeze the lines in because there is an attraction occurring there. So that's the difference between the two. This isn't part of the syllabus, but it's a nice thing to talk about. So this is a little bit beyond, but you might have come across this if you do Year 11 physics, is electron orbital diagrams. What we do know usually in Year 10 chemistry, this is how we depict the electron configuration of oxygen. Now, in quantum physics and quantum chemistry, this is the actual way we represent the arrangements of the electrons. Now, you don't need to know specifically how to draw these diagrams, because that's not assessed in this topic, but I want you to appreciate the fact that if we actually have a look at the structure of oxygen, oxygen is actually paramagnetic. So oxygen is actually paramagnetic, and you can tell because there's two unpaired electron spins, which means that oxygen is magnetic or has the ability to be magnetic, and you can actually achieve this with liquid oxygen. So liquid oxygen, what this man is pulling on here, we have two bar magnets, and you can see the liquid oxygen is attracted between the two magnets. So try that again, and you should actually see the attraction occurring right there. Okay, so oxygen is paramagnetic under really cold conditions. You can actually see its magnetic properties, particularly with liquid oxygen formed there. Next, let's just quickly talk about it. So diamagnetics, diamagnetic materials are unable to form permanent magnets. They tend to repel the magnetic field. The internal magnetic field of a diamagnet align in the opposite direction to an external field. Paramagnets, unable to be permanently magnetized. They are relative weak attractions with the external magnetic field. Its own internal magnetic field will be parallel, aligns parallel with the external field. When the magnetic field is removed, it returns to its original state. So both diamagnets and paramagnets, they don't have a permanent magnetization. We said that ferromagnets, once it's magnetized, it will stay magnetized. That's not the case for diamagnets and paramagnets. One of the interesting things that we actually see in life is that under a lot of really specific circumstances, any object will have its own magnetic field. Remember, the human body is made from electrons. Every material is made from electrons. So deep inside, we all have intrinsic magnetic spin in us. So this was an experiment done, I think, in the Netherlands many decades ago, and they actually demonstrated a frog levitating. Now, this frog is actually alive. The frog was not harmed, but they put the frog in a sort of a little vacuum tube and really had a really strong magnetic field going through the tube, and you can see the frog levitating here. There's an interesting video where they actually levitate other materials, which you can also watch. It's quite fascinating stuff to demonstrate that any object will have magnetic properties to them when exposed to a strong enough field, that is. One of the most famous examples of diamagnets, so repulsion, really weak repulsion magnets, is a thing called superconductors. Superconductors was in the old syllabus, but we don't really talk about it anymore, but it's worth just quickly mentioning. Diamagnets, in the case of potential superconductors, causes a really strong magnetic repulsion when exposed to an external magnetic field. So you can actually use this to propel Maglev trains to make it move very fast. And one of the great things about it is superconductors have zero electrical resistance. So you can have a train moving along the track at really high speeds, and there's no induction of current onto the rails, and therefore there's no resistance on the rails. The only problem with it is it needs to reach a supercritical temperature. Now, supercritical temperature or supercritical temperature is a point at which a material exhibits superconductor properties. There aren't many superconductor materials that we know of, and the best one we have from memory, this has been a while since I discussed it, is about minus 440 to minus 60 degrees Celsius. So you can imagine it's not a really practical application as of yet. So in order to cause this kind of phenomena, the magnet to be repelled against our superconductor, you need the superconductor to be really cold, which you might need liquid nitrogen. And obviously, you can't just supply tons of liquid nitrogen around, even though it's relatively cheap. Actually, a fun fact, liquid nitrogen, I do believe, is cheaper than your average carton of milk. So there you go. Alright, so that concludes our lesson for today. We've talked about ferromagnets, and we also talked about how you can make ferromagnetic materials become magnetized. That actually concludes Module 4 and our inquiry question of magnetism. We will revisit magnetism and electricity again come Module 6 in Year 12. So until then, take care, and hopefully you've enjoyed this whole inquiry point.